Hello there, my name is Anne and welcome to today's video. Last lesson we talked about Eulerian graphs and today we're going to get stuck right into Hamiltonian graphs. Anyway, if you do find this video helpful, please give it a like or subscribe to support the growth of this channel. So with that said, let's get stuck into it. Okay, so we're going to start with a little bit of context. Now, in the early 19th century, there was an Irish mathematician, physicist, and astronomer. His name was Sir William Rowan Hamilton, and he produced this Icosian puzzle. Now, the Icosian puzzle concerns a dodecahedron. That's a platonic solid that has 12 regular pentagonal faces, 20 vertices, and 30 edges. And the aim of this puzzle was to find a path along the edges of the dodecahedron in such a way that passes through every single vertex of the dodecahedron. Now, it's actually this puzzle here and also the traveling salesman problem, which are closely associated with Sir William Hamilton and his work on what we call Hamiltonian graphs today. Before we get into Hamiltonian paths, cycles, and graphs, I just want to mention quickly what the traveling salesman problem is. It's a classic algorithmic problem in the computer science field of study, and it's often shortened to TSP because that's how often it's referred to. And it's all about this situation here. So a salesman is given a list of cities and the distances or costs to travel between all of them, and his goal is to find the most efficient route that visits each city exactly once and then returns him back to where he started. So just a quick review of what a path is. Now, if a walk doesn't repeat any edges, and it also doesn't repeat any vertices, then we can call it a path. A closed path is called a cycle, and these paths and cycles are Hamiltonian if they visit every single vertex. So a summary of all of that is on the screen here. Let's reiterate. A path is a walk where both edges and vertices cannot be repeated. If the path passes through every single vertex exactly once, then it's called a Hamiltonian path. And then we have a specific name for a closed Hamiltonian path that's called a Hamiltonian cycle. Okay, now similar to Eulerian trails, which encompass both semi-Eulerian trails and Eulerian circuits, when we refer to Hamiltonian paths, that includes both an open Hamiltonian path and a Hamiltonian cycle. So an open Hamiltonian path begins and ends at different vertices and visits every single vertex. Now, when this happens, it doesn't need to visit every single edge, it just needs to visit every single vertex. Hamiltonian cycle is basically the same except that it begins and ends at the same vertex. Okay, so a semi-Hamiltonian graph is defined as a graph that contains an open Hamiltonian path only. This means that it does not contain a Hamiltonian cycle. Now, on the graph on the screen here, I'm going to show you how to find an open Hamiltonian path. And there really is no method to this. You just have to use your own spatial awareness and a little bit of trial and error and keep your fingers crossed that it doesn't take you too long to find the Hamiltonian path. So I might start with A and just travel along. I'm making sure that I'm not repeating any edges or vertices. I'm stuck there because I can't go back to A and I haven't reached C yet. So I might try again, maybe am I doing the exact same thing? Okay, now I can't get to E, so maybe I'll start from vertex B, and I can't get through to C. So because I can't get through to C, I might start from C this time. And there we have it, my Hamiltonian path. I cannot connect vertex E back to vertex C, and so it's not a Hamiltonian cycle, but this is a path. It doesn't repeat any edges, it doesn't repeat any vertices, and it passes through every single vertex. I'm sorry, it's a little messy. So let's look at Hamiltonian graphs now. The difference between a semi-Hamiltonian graph and a Hamiltonian graph is that a Hamiltonian graph contains a Hamiltonian cycle. So let's look at this graph and try and look for that Hamiltonian cycle. So I'm going to start at vertex A. That was a complete fluke. I found the Hamiltonian cycle straight away, which means that this is a Hamiltonian graph. Okay, so now that we've looked at Hamiltonian paths and cycles and also what a semi-Hamiltonian and Hamiltonian graph is, we could get stuck into an example. This is an application of Hamiltonian graphs. Let's read the question. Carson is employed as a waste truck driver for the city. The graph below shows the collection points A, B, C, D, E, F, and G, and the distances in kilometers between them. Part A asks us to use mathematical reasoning to explain why the graph is Hamiltonian. Now, the only reason why a graph can be Hamiltonian is if it contains a Hamiltonian cycle. So let's go back to the graph and see if we can find a Hamiltonian cycle. Okay guys, we have the graph back on the screen here, and what we're going to do is look for a Hamiltonian cycle. A Hamiltonian cycle is a closed path that passes through every single vertex exactly once. And this one is really easy. So I'm going to start just over here at vertex G, up to C, B, A, F, across to E, up to D, and then I'm going to end where I started, and there is my Hamiltonian cycle. So because this graph has a Hamiltonian cycle, the graph is Hamiltonian, and that's what I'm going to write down. So the graph contains a Hamiltonian cycle, and I'm going to specify a specific cycle. I know I started at G, but I'm going to label my path or my cycle from A. So I've got A, B, C, G, D, E, F, and A. Therefore, it is Hamiltonian. Now, before we move on to part B, I just want to talk about repeated vertices and the stated path or cycle. Now, when we're looking for repeated vertices, we're going to look in between the beginning and the end vertex. In this case, it's a cycle, so it begins and ends at the same vertex, which means that letter is going to have to show up twice at the beginning and the end. But when you look in between the A's, you'll notice that none of the other vertices are repeated. So we can confirm that this is a cycle where vertices aren't repeated. Okay, part B now asks us to state a possible route that Carson can take to collect waste from each location without revisiting any collection points or driving along the same road twice, and beginning and ending at the depot. Well, I already did that in the previous part, so let's just duplicate that and bring that down. Okay, let's move on to example 2, which is an application of semi-Hamiltonian graphs. Ksenia is planning a multi-country holiday through Europe and has 6 destinations that she would like to visit. The graph below shows the costs of the flights between each location. Okay, so we have a few cities here: Barcelona, Munich, Hvar, Prague, Santorini, and the Amalfi Coast. And you can see the cost of the flights between each of these locations. Part A asks us to use mathematical reasoning to determine if Ksenia can travel to all 6 destinations without revisiting any cities or repeating the same flight path. So that basically means look for a Hamiltonian path where vertices and edges are not repeated. It doesn't specify that she needs to begin and end at the same city. So we're just looking for an open Hamiltonian path at minimum. Now we've got the graph back on the screen here, and I'm going to try my best to look for an open Hamiltonian path, which actually isn't that hard. You can basically just connect all the cities like that. So it is possible for Ksenia to travel to all the cities without going over the same flight path or revisiting the same city twice. And that's what I'm going to write down here. The graph contains an open Hamiltonian path, therefore it is possible. So moving on to part B now. Where should Ksenia begin and end her holiday to minimize flight costs? State the order of the cities that she should travel to and the total cost of her flights. Now, this question is actually quite difficult. The traveling salesman problem that I referred to earlier actually doesn't have a defined solution or a defined algorithm to find the solution anyway, because there are so many different possible combinations to consider to be able to find the minimum Hamiltonian cycle. So I have the graph back on the screen here, and what I'm going to do is I'm going to look at the overall graph and try and highlight some of the cheapest flights, and I'm going to try and include those in my Hamiltonian path. So the cheapest flight overall is this one here from Hvar to the Amalfi Coast. The next cheapest is this $238 flight from the Amalfi Coast to Santorini. The next cheapest is actually this one from Amalfi Coast to Barcelona, but that won't help me find my Hamiltonian path. I'm going to highlight this one here from Munich to Barcelona, $319. Now I've got Barcelona, Munich, Hvar, Amalfi Coast, Santorini. I just need to connect to Prague. And I'm going to do that with this edge around here. And then I just need one more connection for my Hamiltonian path. Guys, this is future editing on here, and I'm so sorry I've got to do this. I wasn't kidding when I said that this question can actually be quite difficult, and especially when you make a boo-boo like I did here. I somehow did not see that I should have completed this Hamiltonian path with that $491 flight between Prague and Santorini. Please bear with me for the rest of this question. I'm going to do my best to overlay the video with the correct solution and to make the audio edit as seamless as possible. Anyway, you wouldn't be learning if you weren't making mistakes, so here I am rectifying mine. All right, back to the question. Might use this. But I'm just thinking, if I didn't use $337 and $491, I would connect Prague with maybe 530 and 450. 530 and 450. Yeah, I'm definitely going to go with the other option. So Ksenia should begin and end her holiday at Munich and Hvar. Now I'm going to label that path. So I'll just start with Munich. We traveled to Barcelona, MB, then to Prague, Santorini, Amalfi Coast, Hvar. And the total cost of that, let's add all this up. So I've got $319, $337, $491, $159, and $238. I'm going to use a calculator and then I'm going to write the total cost. Okay, so the total cost of her flights is going to be $1,544. And that is my question complete. And that's all I have for you for Hamiltonian Graphs today. Again, if you found this video helpful, please consider liking or subscribing, or at least sharing it with a friend, just anything to support the growth of this channel. Next lesson, we'll be talking about shortest path algorithm. Anyway, I'll see you in the next one. Bye.